Hi everyone, this tutorial is Unit 15, working with assembly language. Now, before I start, just to be aware that you need to download a software from the university website, which is called Coco IDE, which I will talk about in a minute. So it's very, very important you understand how assembly language function in a way for you to be able to understand it and complete the exercises. Now, before I start showing you some example, I need to explain or talk to you about what is assembly language. Sometimes we refer to it as assembly code. Other times they refer to it as symbolic machine code, assembler language. Okay. It's normally abbreviated as ASM or .asm, whether it's capital or lowercase. It's a low-level programming language with very strong corresponding between the instructions in the language and the architecture's machine code. An assembly language statement is a line of text that translates into a single machine instruction. Assembly language is expressed in a more human-readable form than binary instructions, and names are allowed for memory location, registers, operations, etc. High-level languages such as C++, Java, also Python comes as high-level languages. So these are some example of high-level languages, while assembly language is more low-level language. So these languages deliberately hide from a programmer many details concerning how the problems actually will be solved by underlying computing machinery. So let's have a look at this example in BASIC. So let's say we have this variable x equal 4, variable 2 we have y equal 5, variable 3 z equal x plus y. So print x plus y equals z. So x plus y equals z. So we know x variable here is 4, we know variable y is 5, and so here basically 4 plus 5 we have 9. Now as you can see here this is basically means all of this here ones and zeros means z equal x plus y. So the C language or high-level languages require a small amount of awareness by the program or the author of how a computation is going to be processed or the execution. So for example, that the main program will get linked with a library of other special purposes, subroutines, instruction and data will get placed into separate sections of the machine memory. Variables and constant get treated differently. Data items have specific space requirement because this is we're dealing with high-level language. Now, key point, high-level languages let programmers focus attention on problem to be solved and not spend effort thinking about details of how a particular piece of electrical machinery is going to carry out the piece of desired computation. So these are kind of good sometimes because the problem gets solved sooner. Also, the program can be written faster. So programmers don't have to know very much about how a digital computer actually works. So here, just to quickly, before we get into details about assembly language, I'm just trying to explain to you why is there's a difference between a high-level language and low-level language. High-level language such as C, Sharp, Java, C++, Python, and low-level languages like we're going to look at it in a minute. So here, just I want to talk to you about computer scientists versus programmers. But computer scientists do not want to know how computers actually work. So we can fix computers if they are break. So we can employ optimum algorithms. So we can predict computer behavior. So we can devise faster computers. We can build cheaper computers, and we can pick one suited to a problem. Machine's own language. So for understanding how computer work, we need to familiarity with the computer's own language called machine language. It's a low-level language, very detailed. It is specific to a machine architecture. It is a language spoken using voltage and human represented with zeros and ones. So assembly Assembly is simply a human readable representation for what will be compiled into machine code. Yeah. So what are we going to compile into the machine language? We use something called assembly. Okay. So let's have a look at this example. This is an example of a assembly language. Yeah. So now we have the machine code, we have assembly language, and we have a high level language. So there are two key ideas when it comes to assembly language. First, mnemonics or opcodes, operation codes. We use abbreviation of English language words to basically reflect that. And we also have symbolic addresses. Yeah. So we invent meaningful names for memory storage locations we need. This makes machine language understandable to humans if they know their machine's design. So let's see at our example program, okay, rewritten using actual assembly language for Intel Pentium, for example, which I'm going to show you that in a minute. So writing assembly language programs. So we have opcodes, operational codes, and we have operands. Each assembly language statement is split into an opcode and an operand. The opcode is the instruction that is executed by the CPU, and the operand is the data or memory location used to execute the instruction. So here we go. So we have this assembly language opcode mnemonic with instructions. So here, for example, here we're using imp for input, output, storage, STA, load, add, subtract, branch, halt here as in to stop or end the actual program, and then we have data here, that data definition when we need to declare data. So here input to input the value, then store the value in the accumulator. We have output the accumulator's content, store. So here we transfer a number from the accumulator to the RAM. Load, transfer a number from RAM to the accumulator. Add accumulator content to the content at a RAM address. Subtract accumulator content from the content at a RAM address. Branch, this is when it comes to looping. So if you are using Java, for example, you use for, and then you start with your, okay, I equals 0, I less than 10, I plus plus. Then when you system.output.print, then it gives you, for example, 0 to 10. So here, because we can't do that, so we have to use something called branch. Halt when we stop basically the process, and data when it comes to declaration. So let's have a look at this. When I mentioned earlier about we're going to look at Pentiums, for example, registers, visible registers. So we have, for example, 4 general purpose registers: EAX, EBX, ECX, EDX. And we have 4 memory addressing registers: ESP, EBP, ESI, EDI. 6 memory segments registers. We have CS, DS, ES, FS, GS, and SS. Instruction pointer and flags registers. We have EIP and EFlags. Now, before we get into details about it, I just need to kind of refresh your memory when it comes to flags, the ALU flags. So the ALU creates and output a set flag of flags from the operation. Many instructions will cause these to be placed into the condition code register. So if you remember from previous units, so we have the flags called 0, C for carry, N for negative, and V for overflow. Okay, so the compiler uses this flag whenever 2 numbers need to be tested and compared for equality. So the Z flag is set whenever the result is 0. The N flag is perhaps the simplest to discuss. This is set to whenever the sign bit is set on the output. The C, or the carry flag, was set above whenever an addition or subtraction require a carry. The compiler uses these flags whenever 2 numbers needed to be tested on compared for an unsigned less than or whenever an extended 64-bit addition or subtraction needs to be carried out. So let's have a look at this assembly code. So we have here section.text. As you can see, this is space, global start, which we're gonna have a look at some examples, then we'll understand it a bit more. So here this assembly code, basically, if we run it, it's just gonna give us print hello world. Yeah. As you can see here, we use semicolon to basically reflect comment. So here I'm telling to the compiler, do not execute this line. That's why I'm using semicolons in this example of assembly language. Okay, assembly code. But for just like in Java, when you use // so that means you tell the compiler, do not execute this line of code. So here, in order to help us to understand, to comment on every single line of your code. So here, just all of this to basically print hello world. Here, as you can see here, the EAX I mentioned earlier about registers, EBX, ECX, EDX, and so on. And here, where I'm just saying basically exit at 0. So here it says that the text section, but now we need the data section to create a string of characters. So we use DB, which stands for declare byte. Don't worry too much about it. Here I'm just saying basically DB to declare hello world in this instance. So EAX is the accumulator, which is the default register for many addition multiplication command. EBX is a base register that stores the base address in memory addressing. ECX is the counter and the internal counter of the repeated prefix command and loop command. EDX is always used to place the remainder produced by integer division. So here we go. So we have the EAX, EBX, ECX, EDX, ECI, EDI, EBP, ESP, and etc. Don't worry too much about it. You don't need to memorize that. Just that's for you if you see it, and assembly code with these registers, so you do not get panicked. You don't understand what's happening there. So at least you have some idea. So general registers on the CPU in 86 assembly language and R32-bit register. These registers can be viewed as variables in C language. Here we go. This is the 1686 registers. I'm not going to get into details about that. So just to basically sum up what I was saying, so assembler is a translator that translates an assembler program into a conventional machine language program. So basically the assembler goes through the program one line at a time and generate machine code for that instruction. So what it does, it translates each line into a machine code. Yeah. So what is a machine code? It's ones and zeros. Generate machine code for that instruction. Then the assembler proceeds to the next instruction. So back again to the operation code and operand. Each assembler language statement is split into an opcode and an operand. The opcode is the instruction that is executed by the CPU, and the operand is the data or the memory location used to execute